Okay, so I guess we'll wrap up. Two more talks today. The first is going to be Deniz Gencaga. He's at Noah Crest at City College of New York and works with Bill Rossow and company. He's going to talk about comparisons of information-theoretic methods to estimate information flow in dynamical systems.
Thank you. Thank you very much. Thank you all for coming. Today I'm going to talk about the information flow in dynamic systems and how we can estimate these by using information-theoretic methods. I'm working with Kevin Cook and Bill Rossow in this project. So in this project, our goal is to understand the Earth climate variability and to understand the relationships between various climate subsystems and which climate variables are related to each other, and especially the directions between these climate variables. Which variable triggers the other variable, and which variable is affected from the other variable. This is the most important thing for us to understand. So here you see a cartoon. We have forces acting on our planet, and our planet has a response on this, and we have complex feedback systems. So it's a highly nonlinear system. There's also a cartoon explaining all these feedback mechanisms. So we're trying to understand this mass, which is highly nonlinear, and see the relationships between these variables. So relevant variables, which climate variables are related? As I said, that's the ultimate goal. So there are two figures here. For example, the relationships between Clausian and linear southern oscillation map here, the Clausian seasonality map here, for example. These are the relationships which were obtained using information-theoretic methods, which I'm going to explain later in the upcoming slides. So let's say we have three variables, and how we can estimate the relationships using directionality. That's the ultimate goal. We can estimate the relationships using traditional methods like correlation analysis. Everyone knows that. Or if you go a little bit one step higher, using mutual information. That's a little bit higher. We can explore the relationships with mutual information too, but none of these methods give you the information about the directionality, which variable causes the other variable to happen. So our goal is to explore this information, which is the directionality. So we're exploring this in this project. So the outline is, as I said, which are relevant of these variables, and then I'll go to the methodology quickly. I'll briefly give you the brief recapitulation of what entropy mutual information are, and then I'll introduce you a new thing which is called transfer entropy, which helps us to determine this directionality information in addition to the relationship information. Then I'll give you two methods which we developed to estimate the entropy and mutual information, but not the transfer entropy. Then I'll go into the transfer entropy in the more detailed section. So I'll go into the next section, which I'll show you the simulations, and then tell you about our ongoing research right now. So information theory. What is information theory? So what we look is we quantify the relevance of a variable to a phenomenon. we use information theory for this. That's the basic, everybody knows about that. What is entropy? Entropy is used to quantify the amount of information provided by a single variable. Mutual information is used to quantify what we learn about one variable from the other variable. These are basic definitions. Everybody knows about these. This is new. How can we identify the causal interactions? So here comes the direction that I mentioned before. So if we have two variables and if information flows from one variable to the other, then there's a direction information too. Then we have to find this somehow too. So this is somehow related to causality, but this is not exactly causality, I have to tell you this. This is a little bit misused concept in the literature, because there can be a third component z which could affect x and y at the background. So we cannot exactly measure causality by using any of these methods, but we can always find the directionality information, I mean the information flow. So I will not use the causality terminology, but information flow throughout this presentation. So in the literature, there are some methods which are data-based approaches. Transfer entropy, it is called. So the most known paper is Schreiber's paper. And there are some methods which are model-based approaches. If you know the model, you can also estimate the directionality. But this is very difficult for us since we're dealing with atmospheric sciences. Atmosphere, I mean, it's huge. I mean, we rarely know anything about that. How can we define the mechanisms and define the relationships between the variables and put a model on that? We're trying to do that. A lot of groups are working on that, but we do not prefer to go in this way and work on model-based approaches. Instead, we're trying to go on data-based approaches and work on observed data and work on transfer entropy, since we do not have full-grown methods yet for everything. So if estimation of information theoretic quantities from data. So in our cases, we prefer using Bayesian methods generally. Why? Because if we use Bayesian methods, we generally estimate the probability density function as a whole in general. And then we can estimate the entropy, I mean the uncertainty about the PDF as well. So we can say that we can provide the error bars, thus provide our statistical significance of our findings in our most true way. So we're not dealing with point estimates. We're dealing with PDFs. So we prefer using Bayesian methods, and that's why we're estimating the PDF first, and then using PDF, then we estimate the entropy using that PDF. That's the entropy estimation part. I'm coming to the transfer entropy slowly by slowly, so I do not want to confuse you. Our goal is to estimate the transfer entropy. Okay? So entropy, everybody knows these equations. This is the discrete version. This is the continuous version. Don't forget the Lebesgue measure, which is very important. And the joint entropy for 2 dimensions. And here comes the mutual information. Okay, here's the problem in all mutual information estimations from data. The plus and negatives, summation of Shannon entropies, marginal Shannon entropies, and the joint Shannon entropy minus the joint Shannon entropy. So in all of these estimations, if you estimate these quantities first, and then do these additions and then these subtractions, you always end up with biases. There's no way to avoid this. There's no single paper that I have seen that there is a way of avoiding this. There are a lot of papers. Grasberger is very famous for this, who add some corrections to these, so that he claims that he can avoid the bias coming from these additions and subtractions, but that's not a good way to do. That's artificial. So in all mutual information estimations by this way, you end up with biases, period. As the previous speaker said, that's a way of statistical independence measuring, because if they are statistically independent, you can say they are zero. Also, it's a measure of statistical dependency measuring. There is something called Dobroshin conditions, if I can spell correctly. As far as I could remember, it's e to the minus 2 mutual information. Then if you use that measure, you can also use that as a statistical dependency measure, the mutual information. That's a side information, nothing related to this presentation. So our goal, transfer entropy. Now direction comes into the directionality measuring comes into the presentation. So how shall we put the direction? Now let's assume that, we have one x variable and it has measurements, and the other variable, it has n other measurements. The transfer entropy is defined by this Kubeck-Leiber divergence. So if you look at this Kubeck-Leiber divergence, the numerator xi plus 1, which is the feature value, depends on its past k values. This notation, please pay particular attention to this one. Here it is defined. It starts from I, and it includes k past values, and y includes its current value and its past L values. So what this equation tells us that this future x value conditioned on its past k values and the other values past L values. And the denominator tells us that this future value conditioned on its past k values. So this Kubeck-Leiber divergence tells us that information that we learn from the past state of one variable about the current state of the other. So we learn the future value of x from the past values of y. Is this clear to everybody? So we're learning the future value of one variable by using the past values of the other variable. So directionality came into the equation by this definition. Okay? We made the mark on this assumption. That's the definition of Schreiber for transfer entropy. So you can define it in two directions, from x to y or y to x. So they are different in two directions. Now the problem. The problem is there are several methods in the literature, which are not too many. You can search them on the internet. There are a few, couple of methods, which are not totally clear on choosing their ad hoc ad hoc parameters. In all of those methods, there are some parameters, and none of those methods tell you why they chose those parameters. Some of them chose, okay, let's say this is 10, and some of them say, okay, let's choose this 0.5. And if you choose something else, let's say 9 or 0.7, then you can never ever get anything logical. So, limited literature, no given information on how to choose the ad hoc parameters. That's the curse of this transfer entropy literature. So, we want to use this method in our goal to estimate the directionality for atmospheric science purpose. So we couldn't handle this situation. Then we decided that we propose using two existing methods in the literature, which are widely used, and propose our own Bayesian technique we developed, and synthesized all of them.
So you're using two ad hoc methods plus your own Bayesian method, and then you synthesize them.
Yep.
But you just criticize the ad hoc methods strongly. But you're going to use them anyway.
Yeah, then I do, but the ultimate result that I'm going to come at the end of the presentation is that at the end, I always play with their parameters, and I first use my method and find the result with the data. Then you use their method and find results with their data. I feel with my data again. If they agree on the solution, then that means that the parameter that I chose for their method is okay. But if that's not okay, then I have to play with their ad hoc parameters until they agree. That's the only way that I could find their ad hoc parameter range. And that could be computerized. There's no other way to find their parameter. Because I mean, if you just get a method from the literature, and there's no way that you know how to choose their parameter, then if you get the result, how can you justify the solution that you get? There's no way if it is correct to say if it is correct or not. So this is a way of somehow justification. So transfer, okay, method one. How can we estimate the entropy by using our methods? So as I said, first we have to estimate the PDF, right? This is a piecewise this is called piecewise constant model for probability density function. So to make things simpler, I'm going to call it histogram for the moment. We approach the PDF, approximate the PDF as a histogram, and then from that histogram, I'm going to assume a Bayesian model to that histogram and take samples from that histogram, couple of samples from that histogram model. That means taking samples from that PDF. This concept is very complicated. So you have a model. Let's say I have have a histogram, okay? But this is not a regular histogram that you know. This is a Bayesian model actually. So this section has a probability. This section has a probability. This section has a probability. What I mean by probability is the height has a density function, has its own density function. This height has its own density function. This has its own density function, and it goes on. So what I do is I assign PDFs for each piecewise constant sections, and then since these have PDFs, I can sample from PDFs, right? So if I sample 30 samples from PDFs, then what I do is at the end I sample from 30 samples from this whole PDF, right? So at the end I can have a mean and standard deviation for a PDF. That's how I obtain the error bars. Anyway, this is how we obtain the error bars and the mean for a PDF. And so once we obtain the entropies and in that way, then we can estimate the transfer entropy using these equations, because transfer entropy could be explained as a summation and subtraction of individual Shannon entropies in this way. Oh, all right, okay. That's the thing that I explained just here. Infer the PDF of data, sample PDFs, estimate the entropies, and obtain the mean and standard deviation. Okay, so I'm skipping this. And this is the Bayesian modeling of probability density function. Everybody knows the Bayesian formula. So this is the posterior, this is the prior, and this is likelihood, this is evidence. So this is how we do our updates using the prior and the likelihood. So let's say that we have our histogram here. This is two-dimensional, and we estimate the entropies by using our PDF estimates. So these are the, for example, results of samples that I got by sampling from the histogram n times, and I got the mean and the standard deviation. So at the end, this is the posterior. So since I can sample, I have a posterior PDF equation which I can sample from. So if you look into this equation, for each bin's probability, we have a mean which have plus 1/2. So if we have 0 filling in a histogram, we add a plus we add a half, even if we have 0 occurrence in that histogram bin. So this way we smooth the histogram somehow. That's why it's more accurate than using regular frequentist histograms. That's why we use this Bayesian approach. Is this clear somehow? Yeah?
So you're also, I see an end dependence. So you're using this also to determine the number of bins?
Yeah, M has also a prior, which is common, which is uniform prior.
And you're taking a flat distribution over the
Over the pi? No, pi has,
it's flat over the simplex.
no, pi has Dirichlet distribution.
Okay, yours like fixed shape.
Yeah.
Well, we'll talk about that. I think that's a problem if you want to estimate it.
Estimate what?
If you want to determine the number of bins, you can't use a Dirichlet distribution with a fixed shape. You have to use a process. You have to have the shape frame to depend on the number of bins.
on the number of bins? That might be, actually we can talk later after the talk.
Yeah.
Because it has some problems, which I'm going to show later. So how we can find the optimal number of bins? We also find the number of bins by doing some calculations. We choose the maximum number of bins, which maximizes the posterior, and determine how many bins to use for the histogram. This is the easiest question to ask if you use histogram. I mean, if you ask a scientist how many bins do you use for using a histogram, for example.
The number gives me what I want.
Yeah. So let's wrap it up. Oh, I generalize it to put a beta here instead of 1/2, and generalize it, and explore the effect of beta, which is the beta constant here at the Directionality prior, and we also explore the continuous model instead of the histogram piecewise constant model, and looked in that way and compared the results. The piecewise constant model has very poor results, as you see. So we can that might be due to that reason. Estimates within one standard deviation, the error bars is 29%, which is very low. But once we use the mixture of Gaussian's model, the continuous version, which I have no time to go into, we use a nested sampling of our colleague John Skilling, which is an MCMC method. We use that also. It gives us 68% within one standard deviation. But the drawback is this computational very slow, whereas the histogram method is very fast. So the second method for the transfer entropy estimation. I told you that the sum of individual entropies to estimate the mutual information has a major drawback because of the bias problem. So in order to avoid that, Fraser and Sweeney and Darbella and Wajda proposed another method for mutual information estimation, not transfer entropy estimation. They proposed using adaptive bin widths to estimate the mutual information, and that really gave better results. They showed it on Rossler attractors in the paper, Fraser and Sweeney, and that's why I took that method and used this equation. Since they use it in mutual information, I took that and estimated transfer entropy by using the mutual informations, using their methods. And this mutual information estimation method is available on Peter Tucholsky's website. So by estimating transfer entropy in this way, is much better than histogram methods. The other method is kernel density estimation methods. So in this way, we do not divide the data into ranges as in histogram or adaptive bin, adaptive partitioning methods. Instead, you place a kernel at top of each data point. Then you estimate something called correlation sum, which is well known in the chaos theory literature. I do not go into the detail, but there's something called radius here. Then the problem is how to choose this radius. In histogram, you deal with how to choose the bin number. Here, you deal with how to choose the radius. So now let's go into this problem. First, you form a curve using Grasberger and Procaccia algorithm. It is in this. It is called this way because they invented it. We observed that the results are too sensitive because you need to find a linear section, and in that linear section you have to pick a radius value to be your radius value. But okay, they say any value in the linear section is okay, but I tried a lot of values in the linear section, but if you just go away from the optimal value a little bit, even if you are in the linear section, your results totally go crazy. So it's highly sensitive. So just saying it should be in the linear section is not a way that you can pick up a true radius value. So hopefully I found this picture. They also propose using mutual information, time lag mutual information, and say that you should find the first zero of the mutual information to find the most uncertainty and use that value as the K of the transfer entropy in the equation. Remember the K value here? Past values of the X variable. By the way, L is always taken to be 1 in all papers because this is a still ongoing research issue. We're also investigating that, by the way. This K and L, how should they be picked? I'm still dealing with the K now, right now. It's highly complicated. So then plot the logging versus the correlation curve. Let's see those. Now, example. This is coupled linear autoregressive signals. Let's see. This Y signal couples the X signal by this E coefficient. Okay? They are linear. Very simple example. Everything is Gaussian. And I formed this curve I mentioned. So this is the linear section. So I estimated the mutual information like this, and the first place that it touches 0 is approximately time lag at 10. So what I do is I first take K and L to be 1 and estimate the transfer entropy from X to Y, which is blue, and Y to X, which is red, both directions. These are the log of radius values. I'm sorry, they are so small. I'll tell you the values. And then I take K equals 10 from this mutual information, and L equals 1. Now, if I compare these two curves, when log E equals 0.37, which is here approximately, I see that the blue curve is higher than the red curve. If I look here, 0.37 here, the blue curve is higher than the red curve, but for the left section of that, the blue curve is still higher than the red curve, but for this figure, the red curve is higher than the blue curve for the left section. So there's a mismatch for the left-hand side of this radius value. However, for the right-hand side of this value, they totally agree. So the least value that I can take in this linear section, the least value that I can take for these sections to agree is 0.37. That's how I pick my radius in this complicated method. So these are the comparison of the methods. 10 minutes? Okay. So this is the adaptive partitioning method. The black curve is the analytical true solutions. The blue curve is Tyx from y to x, transfer entropy from y to x, and x is the transfer entropy from x to y, which should be 0 because y couples x. X doesn't couple y. So this gives a little bit bias here, as you can see. They are all 0 in the other methods. By the way, this is our method for beta equals 0.5 and beta equals 10 to the minus 10. So as you can see, we have a bias for lower coupling values. The x-axis is the coupling value. So we can see that they are okay, but we have a problem in case of this selection of beta value in our methods. Now, Lorentz equation, we apply this to Lorentz equation, which is nonlinear, as you know, and it is a model which is used in climatology and as a very simplistic model. And here, x denotes the convective velocity, y denotes the vertical temperature difference, and z denotes the mean convective heat flow. Now, since I have 10 minutes, just for 1 minute, I want you to think about these equations to guess which variable could affect the other variable in these set of nonlinear equations. If x affects y, or y affects x, or z affects y. Can anybody say something by looking at the equations?
Maybe z affects y, y affects z, x, something like that.
Why?
Like, because you see the dependence.
Z affects
Y
y?
appears in, z appears in y, and then z does not appear in the x dot, something like
Z affects y, right? You said.
that. Z affects y,
Okay.
and then y affects x,
Y affects
x,
x. But y also affects.
z. I don't know. Just guess.
No, there. No. Okay, I'm skipping. It's not that easy. They're all. Since it's nonlinear, it's impossible to do that. Now, when we apply the methods, all three methods, this is kernel, this is our method, this is the adaptive partitioning method, this is the result. Why? The temperature difference affects the velocity. Velocity triggers the heat flow, and also temperature difference triggers the heat flow, which makes sense in terms of physics, because temperature difference affects velocity. It also affects the heat flow, and velocity affects the heat flow. That's true. So all directions between pairs agree. In subchaotic regime, when you change the R value, again, all these values agree, and the directions are the same again. So again, it's true. Yeah?
So I guess one thing you should point out is that the numbers don't agree, but you've computed the transfer entropy from y to x and from x to y. And the point is that y to x is always greater than x to y in each of the pictures. I just want to make that a little clear.
Which one? Y2x is always greater than y.
Yeah, I just wanted to make clear that the numbers don't agree from method to method, but the fact that the transfer entropy from y to x is always greater than the transfer entropy from x to y.
Oh yeah,
in each of the figures.
thank you for
That's true
reminding
for the
that.
other
Yeah.
variables,
Yeah, there is a problem. So if you look into the comparison of the methods, the directions all agree for every method, but if you look into the magnitudes, they are the same, but the directions are always I'm sorry, the magnitudes are different, but the directions are always the same. So there's a quick application of mutual information estimation. This is not transfer entropy estimation. I can skip this if you wish, because this is not transfer entropy
Yeah, 5
estimation.
minutes including questions.
Okay, let's go to the conclusions then. Oops. Conclusions. So we, as I said, synthesized the transfer entropy methods in the literature, and that's how we chose the other methods parameters, so that when all of them agree, we can use them with our data. By the way, we have just started to apply them to our skip data to use them in the better understand the Madden-Julian oscillation.
What's SQ?
SCIP is International Satellite Cloud Climatology Project. So the main reason that every algorithm currently has a point which needs to reason. The main reason is that we go into this direction is that every algorithm has a atomic parameter, as I told you. Oh, the other thing is K and L value exploration is a huge research direction that should be done. Also, the normalization has to be done because, as you saw, the magnitudes differ. So there must be a research which should be done to normalize the transfer entropies between 0 and 1 or something, so that everything can be compared more logically. I mean, the directions are okay, but the magnitudes are a little bit complicated issue. And currently, all three methods work perfectly direction-wise, so we can make use of them in our research. And that's what I'm saying. We have just started using them in our data analysis from using satellite data. So thank you for your attention.
Okay, more questions for Dennis? I think you need to have more self-confidence about your method, because this idea for me of comparing the two methods you have no respect for, and then trying to fit their parameters, which you think are crappy, sounds ridiculous. So just stick to your method. If you believe it's the best way to go for it, and forget those other people. You've got so much to do already. I don't think you should mess around with those things. That's what I think. I mean, you have a lot of problems to solve here. Am I wrong? What do you think, Kev? Doesn't he have enough to solve already?
This is a horrible problem. This is worse than the pop problem. I started working on this, 2001, when I came here to GIST, and I got a grant from the IST to work on this. We worked on it for a few years, and we had some success with the mutual information business that some of which is there, and that this is when he joined me as a postdoc, and finally he got a position here with Bill Russell to continue this, and I said, well, have fun, because it's an awful problem. The literature is a mess. The estimating entropy from data is extremely difficult because your error bars in the PDFs are very, very small, but it ends up with extremely small error bars in the entropy, which are actually artificially small. So you can't even estimate your errors properly. It's horrible. Dennis has made a ton of progress on this, but it's, you know, he's pinned down where things are bad. Yeah, it's a horrible problem. But I think the transfer entropy results he found are very nice. I think the directionalities are all right, and they agree with the physics. Like what he was trying to show with the nonlinear equations is that they're coupled. So even if you have the equations, you can't see from the equations what variables are driving which other variables. It's not obvious from reading the equations. It's your knowledge of the physics, knowing that temperature differences drive heat flows, right? Drive flow. And if you know that, then you remember what the X, Y, and Z stand for in the Lorentz model, which is a model of a atmospheric column that's tumbling. Then you can make a prediction as to which direction the transfer entropy should go. But I was really excited to see that he actually got the right directionality. That was awesome. So it's horrible.
I think you need to add another slide like Josh had yesterday that said, at the end I'm going to lie on the couch and you're going to help me.
That's right. But Kevin, part of what's interesting, and Dennis, what's interesting about what Mark just made is that the system of equations is just a system of equations. And this result doesn't have anything to do with the physical interpretation of those variables. So there's somehow a sense of direction in that system of equations, but it's nothing to do with the physics.
Oh, wait, I don't understand.
I mean, he calculated these there wasn't any part of the calculation of the transfer entities that depended on the fact that, you know, X was a temperature and Y was something that physically we know is causally.
Oh, right. Well,
It's just a property of that system of equations, not of the physical of the variable.
Right, but the reason the equations come from the physical ideas. The equations came from the physical relationships, but then by the time you get to the equation representation, you can't see which you can't even disentangle it. It's so nonlinear and so coupled. But then the transfer entropy disentangles that for you. It's not neat.
Exactly.
Yeah.
Okay, well thanks for showing us that really